Okay, so we are moving on to a new chapter in our parent class, and we are talking about historical numeration systems. And both in chapter 4 and also in chapter 5, when we talk about number theory, we're going to be dealing a whole lot with division with whole numbers, specifically dealing with division and remainders. Now, this should be an old topic for you. This goes way back into elementary math, where you're learning kind of the four basic operations of addition, subtraction, multiplication, and division. Now, the thing that happens in grade school when you learn division is you're taught how to do long division, and you're taught to write down your remainder, if there is one, in your answer. So you have a quotient and a remainder. And then shortly after that, you're taught how to convert that remainder into either a fraction or a decimal. And a lot of times people learn this in grade school and on through middle school and whatever comes after for you. And they fall under this impression that the remainder idea is a basic idea that's meant to be done away with once you learn about fractions and decimals. And it turns out that is very far from the truth. That concept of a remainder in division is extremely useful in higher areas of math, namely number theory and some other things that we're not really going to look at in this class, just because this is a basic overview. But all that is to say is that if you don't remember how division with remainders works, we're going to review that here. And we're not turning anything into decimals, we're not turning anything into fractions. We want to keep those remainders intact because they tell us something useful in a number of different applications. So all I'm going to do here is walk through a couple of long division examples just to sort of remind you of how long division works if it's been a while. And then we're going to do a little word problem down here that's going to involve long division. So if you don't remember how long division works, it's sort of a four-step process that you cycle through until you're done. So the first thing that I do is I look at the number that's called the divisor. This number right here is called the divisor, and I'm trying to figure out how many times this number goes into this number, which we call the dividend. Now, simply guessing how many times 25 goes into 10,495 is difficult to do off the top of my head. And I don't want to resort to a calculator because that defeats the purpose of this whole exercise. So instead what I do is I start by looking at the leftmost digit. Is 25 small enough to fit into 1, or does 25 go into 1? No, 25 is too big. So then I give myself more digits to work with. Now my dividend looks like a 10. Does 25 go into 10? Well, no, 10 is too small. So then I give myself another digit to work with. Ignoring the comma, this is like saying, how many times does 25 go into 100? 4. Well, I know it would go in 4 times because 4 times 25 is 100. 4 quarters makes $1. That's how I remember that. So the first step is a division step, which is how many times does this thing go into this thing right here, 104. It goes in 4 times. The next step is a multiplication step. I take the number that I wrote up here, multiply it to 25, which gives me 100, and I write that underneath the 104 that I was using in the previous step. Okay, so a division step happened first, a multiplication step happened second. The third step is a subtraction step. I subtract the 104 that I used in the beginning from the minus the 100 that I just got. That gives me a 4. Okay, the fourth step is what I call the bring down step. You go to the next unused digit in your dividend, which in this case is a 9, and bring it down next to the 4 that I got as the result of my subtraction in the previous step. And that's the fourth step. We go back to the beginning again and redo this whole 4-step process using the 49 down here as my new dividend. So then I say, how many times does 25 go into 49? Well, it doesn't go in twice because 2 times 25 would be 50, and this is just slightly smaller than 50. So it only goes in once. That 1 goes up here. And then I do the next step, which would have been multiplication. 1 times 25, which is 25. I do the subtraction, which gives me, in this case, 24. Okay? Now, something that you can do when you're doing long division to sort of do a quick error check on yourself, which is a way of making sure you didn't make a mistake, Every single time you get to this subtraction step, the number that you get as the result of your subtraction has to be smaller than your dividend. Even if it's just one smaller like I got here, it has to be smaller. It cannot be equal to your, I think I said dividend, your divisor is the word I meant to use. This number has to be smaller than your divisor. And the reason for that is because if you get something as big as or bigger than your divisor, then that would have meant that 25 could have gone into this number, 49 in this case, more times than I guessed it did. Okay, and see if you can reason out why that's the case. So I'm not concerned. 24 is smaller than 25, which is what should be happening. I have one more digit to bring down, and now I have 245. Okay, and again, I repeat those steps. So 25 goes into 245 how many times? Kind of like I said before, with 25, I like to think of quarters as in money, and think of this as $2.45. It's close to $2.50, which would be 10 quarters or 10 times 25, but because it's slightly smaller, it's not 10, it's going to be 9. 9 times 25 is 225. That's what 9 quarters would be equal to, $2.25. Doing my subtraction, I'm going to end up with 20 here. Now, there are no more digits to bring down. So this is the step where I call it done, and I would write down my remainder. This number here is my remainder, so I'm going to write an R. I've done it both lowercase and uppercase. I don't care which one you use. I'm using lowercase here. Remainder of 20. If you were trying to get a decimal as an answer, then what you would have done here is if you get anything other than 0, in our case we got 20, then I would add a decimal to my dividend and start adding zeros and bringing those down. And then I would continue that process, putting a decimal point up here and writing all my new digits to the right of that decimal point. But we're not using decimals here. And we're not converting this remainder to a fraction either. So this is how I'm writing my answer. So terminology, once again, I said that this thing, the 25, is called the divisor. This thing, the 10,495, is called the dividend. But in my answer, I have two more terms that are important. The 419 is what we call the quotient. It's basically how many times 25 goes in to 10,495. It goes in 419 times. However, it doesn't go in exactly 419 times. It goes in 419 times, and then there's a little bit left over, and the remainder is that little bit left over, 20. So all four of these numbers can be related by rewriting what I just stated in terms of a mathematical equation, which is this. The dividend, 10,495, is equal to my divisor times my quotient. So 25 times 419 plus my remainder, 20. Okay? So what I'm doing is I'm illustrating what the meaning of these four numbers are in relation to each other. This is basically saying, like we said over here, 25 goes into this number 419 times, but if I did this multiplication, I'm going to come out just a little bit short. I'm not going to fully reach 10,495. I'm going to be off by 20, so adding 20 gets me to that dividend. Okay, let's do the same thing over in this problem. I have 72,108 divided by 36. So same process. 36 does not go into 7. 7 is too small, but it does go into 72. In fact, it goes into 72 exactly twice. 2 times 36 is 72. And so when I get to my subtraction step, subtracting gives me a 0. Next up would be my bring down step. So I bring down a 1. Now, every time you bring a digit down, you have to then put something up here. But looking at this, 36 does not go into 1 because 1 is too small. So what am I supposed to write up here? Well, another way of saying what I just said is that 36 goes into 1 0 times. Notice I'm writing the 0 directly above the 1 that I brought down right before this step. Okay? Things should line up like that. So now that I've done that, there's no point in doing 0 times 36 because that's only going to be a 0. And then when I do the subtraction, 1 minus 0 is just going to give me a 1 again. I already have a 1 here. So what's the point of using up more space to tell me what I already know? Instead, I'm going to jump up to the next bring down step. I'm going to bring that 0 down, which gives me a 10. Same issue occurs. 36 goes into 10 0 times, so I'm going to write a 0 there. Okay, and as before, there's no point in doing 0 times 36 because it's not going to tell me anything new, so I'm going to bring down one more digit. How many times does 36 go into 108 now? Well, 36 goes into 108 exactly 3 times, which you could check by doing 3 times 36. That would be 108. So now, when I do the subtraction, I get 0. When we get a remainder of 0, I don't need to write our 0 here. I can just leave this as is. And rewriting things in terms of this equation like we did up here, my dividend, 72,108, is exactly equal to my divisor, 36, times my quotient, 2003. Now what this means is that 36 divides 72,108 evenly. In other words, 36 goes into this number evenly, and there's nothing left over in the form of a remainder. That's a very, very important concept that we're going to use a lot more in chapter 5, but I'm going to use it also in this little word problem down here. I made a mistake here when I wrote this out, so I scribbled that out. Starting here, it says, a team of 13 adventurers discover a chest containing 974 gold coins. Can they divide the coins evenly amongst themselves? So to answer this question, I can do it by performing a division problem. In other words, I'm going to divide the number of gold coins by the number of adventurers, because the quotient in that case should tell me how many gold coins go to each adventurer. And if there is a remainder, that means that after splitting up all those gold coins, there's going to be less than 13 that are left over, which if we're going to divide those amongst the 13 adventurers, we're not able to do that fairly because not everybody would get one more. So in order to answer this question, I'm basically just going to do the division, and if I end up with a remainder other than 0, then the answer to this question is going to be no. If my remainder does come out to 0, then that means 13 divides 974 evenly, and then that would mean I can divide these fairly amongst these 13 adventurers. So doing the division here, I'll do right here, 13 into 974. Okay, so 13 does not go into 9 because 9 is too small. It does go into 97. In fact, it goes into 97 7 times. Now at this step here, if you're a little rusty on division, this might take a little bit of guesswork. You might have to make some initial guesses. When you say 13 goes into 97, you might guess something like 5 first, and then you would check it off to the side. 5 times 13, you would get 65. That feels too small. So then you might try something a little bigger, 13 times 6, and check that. Eventually you would land on 7, okay? 7 times 13 is 91. And when I do the subtraction, I get a 6. The next step is to bring down my 4 and do the division step one last time. So you might remember me just saying 13 times 5 is 65, which is a little too big. So 13 does not go into this 5 times. It must only go into it 4 times. Okay? 4 times 13 is 52. So when I do the subtraction, I'm going to get 12. Notice I get a remainder of 12. Okay? So what does this tell us? Well, if we divide those coins up evenly amongst the 13 different adventurers, then each adventurer is going to get 74 gold coins. But there's going to be 12 coins left over after dividing those up. And if there's 13 adventurers and only 12 coins, I don't have enough to give each adventurer one more. So the answer here is no, they cannot divide these evenly amongst themselves. And it's the remainder that told us that, not the quotient. So that's kind of one of the reasons why remainders are important. They can help us answer questions like this. Okay, that's going to wrap it up for this week.